Hi everyone, I'm Dr. Sudipta from Department of Physics, Vishwabharati. First of all, I would like to thank the organizers for giving me this opportunity to present my work here. I'll be talking about interacting dark sector and also discuss whether it can provide a possible resolution to the Hubble tension problem. So a cosmologist's wish list is to understand the evolution of the universe starting from inflation up to the dark energy dominated. The empirical evidence for the acceleration of the universe is already well established. We know that around 70% of the energy density of the universe is comprises of dark energy, around 23% comprises of dark matter, and the visible matter only consists of only 5%, which we know. So almost 95% of the energy budget of the universe is unknown. And it tells us that the universe is accelerating. So if the universe is accelerating, obviously one would like to know what is the reason behind this. So there are mainly two avenues along which people search for the reason behind this observed accelerated expansion. One is to consider modify the theory of gravity, and the other way is to consider that there is some new substance which will provide gravitational push rather than gravitational pull and will provide this accelerated expansion of the. And a large number of models have been proposed to be a candidate for this dark energy. So if we consider that the general theory is the correct theory of gravity, then the simplest candidate which can serve as a dark energy candidate is the cosmological constant model. And for in lambda CDM model, what we consider is the cosmological constant is the driving force behind this accelerated expansion. So in a cosmological constant model, what we consider is the contribution from the dark matter component, from the matter sector. There is a contribution from the dark energy component, and also one can consider contribution from the radiation sector. But since the radiation energy density is very small, we often neglect it. So although the lambda CDM model is the simplest and the most popular candidate as a dark energy model, it has been found that this lambda CDM model, when it is constant to different observational data, it reaches the most of the observational data pretty well, especially the CMB, BAO, and the super. However, the cosmological constant suffers from the cosmological constant problem, which is basically that the value of cosmological constant lambda, which is obtained from theoretic aspect, and the value of lambda, which is obtained in the cosmological constant, there is a huge discrepancy in the two values. And this problem is known as the cosmological constant. But apart from this, recently the cosmological constant problem is facing another problem, which is known as the Hubble tension problem. So this plot tells us that the value of the H0, which is the current value of the Hubble parameter, the value of H0, which is measured from the Planck data, and the value of H0, which is measured from the Shoes data, these two from the local measurements like Shoes data, there is a discrepancy in the two values. And so the values which are obtained from the Planck data, in the Planck data, the background model is the lambda CDM model. And in the Shoes data, it's basically the measurements are done in the model. And there is, at present, there is almost 5 sigma discrepancy between these two values. So for Planck value, for Planck data, the value of H0 comes out to be around 66, 67, whereas for the Shoes data, value is around 73, 70. So people has to look for some cosmological model such that the Shoes data. Now, the question is, why are we interested to know the value of H0 so precisely? The value of the Hubble constant is one of the most important parameters in cosmology. So it tells us about the age of the universe. It provides us the energy budget of the luminar sources. It helps us to constrain the masses of galaxies and clusters. It also helps us to put constraints on different cosmological parameters, like it helps us to put constraints on dark matter. Precisely knowing the value of H0 is very important. Now, obviously, one question may arise: is there any discrepancy in the measured data sets? But both the teams say that means they till date they are claiming that there is no discrepancy in the data set. So if there is no discrepancy in the data set, that means one has to look beyond the lambda CDM. And there are a number of models which are proposed as an alternative to this lambda CDM model, like the dynamical dark energy model, the parametrized dark energy model. So in this talk, I'll be mostly talking about the interacting dark energy. So if we consider that the scalar field is our dark energy component, then the Lagrangian for the scalar field is composed of the kinetic part and the potential part, and from that one can obtain the energy density for the scalar field by this one, and the pressure component for the scalar field. This one. Now, with for the dark energy model consisting of scalar field, one can write down the Einstein field equations for a FRW, especially at FRW universe in this one, while we have contribution from the matter sector, and we have the contribution from the dark energy sector, which is basically the scalar field. So we have contribution from the matter sector and the dark energy. And also we will have the conservation equation for the scalar field, which is given by this. So if it's a non-interacting case, means if we do not allow the dark energy sector and the dark matter sector to interact among themselves, that obviously the two components will be conserved by itself. This is the conservation equation for the scalar. Now in parametrized dark energy models, what is done is one can consider the parameter, one can consider functional form for any of these cosmological parameters, like say Hubble parameter, which provides us the rate of expansion, the deceleration parameter, which provides us the rate of acceleration, or the equation of state parameter, which provides us the description of the scalar field dynamics. So obviously all these parameters are interrelated, but if we choose functional form for any of these parameters, then from this one can construct the background dark energy model. And when this dark energy model is confronted with observational data, one can find out the values of these parameters. So this is the strategy that is followed in parametrized dark energy. Now, if we consider that these two sectors, the dark energy and dark matter sectors, are interacting among themselves, then the corresponding conservation equations will get modified. And the conservation now, instead of zero, we will have a non-zero term as the source term. But this overall, the total energy of the system will be conserved, because these two will, if we add them together, the total net component. Now, why do we want a dark energy, dark matter interaction? First of all, is nothing is known about these two components. Interaction between the dark energy and dark matter component will provide a more general scenario. And also it can provide a solution to the cosmological coincidence problem. As I mentioned, that the dark energy component becomes dominating very recently. So obviously, one question can arise: why is the dark energy component becomes dominating only very recently? So if the two components are allowed to interact among themselves, then one can have an answer to this. So instead of zero, now we'll have a source term on the right hand side in this interface. Now, usually the form of Q is chosen phenomenologically, and the popular choices of Q are that it is either proportional to H times rho m, or it is proportional to H times rho dark energy, or a combination. Now, why this particular forms? The reason is one can understand mathematically. If you look at this equation, suppose the conservation equation, then one can understand if this equation has to be dimensionally correct, then on the right hand side one should have a quantity which should have rho m, and something which should have dimension of inverse of time, and the well-known component is the Hubble parameter, which have the dimension of time. So these phenomenal choices are the most popular ones. Obviously, it would have been better if one could obtain the form of this interaction directly from the action. Till now, I have come across only one paper by Liu and Suzukawa, where they have considered a very special case where they have considered the potential to be exponential, and so the source term also comes out to be exponential, where they could obtain the form of this interaction term directly from the lecture. But that may be an artifact of the choice of the potential, because an exponential potential gives us an exponential source term. But otherwise, it becomes very difficult to obtain a source term, the form of source term directly from the Lagrangian. So we resort to these phenomenal choices. Now, if you look at this particular interacting model, where Q is this is a paper by Valentino et al. So if you consider the Q to be proportional to H times rho dark energy, and what they have chosen, they have considered the equation of state parameter close to -1. They have considered some constant value of the equation parameter. And when they confronted this model with different data sets, they find that the value of H0 comes out to be, for some of the data sets, they could obtain a value which is closer to the shoe state. The value of the choice or value of epsilon. Epsilon, as you remember, it basically provides us the strength of interaction. So this value of epsilon, they found it to be of the order of 0.5 and etc. Similarly, but this is the control plot for this. The value of A0, it comes out to be asset, but the value of epsilon is around 0.5, 0.6. People have also worked on some other forms of Q, which is proportional to H times rho dark energy, but the functional form is different. And for that also they could obtain, for some of the datasets, they could obtain some higher value of A0. But again, if you look at the value of epsilon, the epsilon value is around 0.2, 0.5. So the value of strength of interaction is quite high. So what we consider in this particular paper, we considered a mathematical choice for this Q. So we also choose Q to be proportional to beta. So instead of epsilon, we have chosen beta. So beta times H rho dark. And we consider a particular unjust for this interacting model. So we choose a particular parametric form for the dark energy, the equation, the energy density for the dark matter. So which will provide us, in turn, which will provide us the equation of state parameter for the dark energy in this form. So this unjust, it has been shown that it leads to a double exponential potential model, and these double exponential potentials are well studied in the context of inflation as well as. So what we found that for this particular unjust, what we obtain is that for smaller values of A, it will behave like a lambda CDM model, and as we go higher, at the present time, it basically deviates from the lambda CDM model. So this model serves as an alternative to this lambda CDM. Now, for this particular model, we wanted to look at the strength of interaction. So what we considered is that we have chosen, remember beta is the strength of interaction. So we have chosen different values for beta. In the first case, we have chosen the value of beta to be around 0.1, whereas for case 2 or case 2, we have chosen the value of the strength of interaction to be quite small, 0.001. And lambda and gamma, the two other parameters for the proposed model, we choose some arbitrary value. And we've chosen some different ranges of this. And what we have found is that if we look at the evolution of Q, we find that obviously it is different from the blue one. It basically represents the lambda CDM. So as we go on, for case 1, remember the strength of interaction is high. So as the strength of interaction is higher, it is basically shows some deviation from the lambda CDM. And same thing is for the, but obviously the dark energy sector or the dark matter, initially the matter sector was dominating, and then gradually the dark energy sector starts on. So it provides us the correct cosmological. But if we look at the density contrast, the matter density contrast and the dark energy density contrast, what we find that when for case 1, the strength of interaction is quite high, the density contrast is higher, whereas for the other two cases, one cannot find much difference with the lambda CDM. Similarly, if you look at the dark energy density contrast, one can find that for the case 1, it shows a large fluctuation in the density contrast as compared to the smaller values of interaction. So it tells us that, and remember the value of the strength of interaction we have chosen is 0.1 for this case 1, whereas for case 2 and case 3, it's. So if one looks at the matter power spectrum or the temperature power spectrum, what we obtain is that for case 1, one can see there is either there is a suppression in the temperature power spectrum, or there will be enhancement in the matter power spectrum. But what we want to emphasize is that if the strength of interaction is of the order of 0.1 or so, then obviously one should see some imprints in the matter power spectrum. But we do not see such imprints in the CMB matter power spectrum. So the strength of interaction, it cannot be very high, it cannot be as high as 0.1. And so the claims which are being made by other authors that the value is of the order of 0.5 and so, it does not justify, because if the value of interaction is such high, one should have visible imprints on the. However, if we we have also confronted the model with the various observational data. So we have found that the value of H0, it comes out to be around 65, 63. So it could not resolve the Hubble tension. The value is closer to the Planck value, but the strength of interaction is very close to 0.01. So the strength of interaction for these interacting models comes out to be, as if we consider observational data, it comes out to be very small. We have also considered another parametrized model where this Q is considered to be the same form, And we have considered a linear parametrization for the equation of state parameter. From that, one can obtain the equation of the component for the energy density for the scalar field, and from this one can also obtain the matter density for the matter. And from if we use these two components, one can find out the value of this H. So here this beta W1, beta W1, these are the H0, these are the model parameters, and we have chosen the value of omega m0 to be around 0.3, 0.27. So if we confront the model with different observational data sets, what we find is that the value of H0, it comes out to be higher. It's around 75, 74. At least for Hubble plus CC. For some of the data sets we obtained that is higher. But the value of epsilon, what we obtained is again, it's very low. It's around 0.01 or 0.05. And what is interesting to note is that if you look at the sign convention, sign of this epsilon, the sign is negative, which indicates that energy is transferred from the dark energy to the dark matter sector, not the other way around. We have also plotted the effective W, the equation of state parameter. E is basically H by H0 for different data sets. So what it shows us that this horizontal line is for W is equal to -1/3. That means that's in the line of acceleration. So at present, the universe is accelerating because it is below less than -1/3. But in future, it will again proceed to a decelerating phase. So it W effective shows a transition from deceleration to acceleration phase, but it again indicates towards future deceleration. Now, since the flow of energy density is in the opposite direction, we have also plotted rho phi and rho m for this particular model, and the solid lines represent the energy density for the dark energy component, whereas the dashed line represents the energy densities for the dark matter. So, what it shows that although the flow is from the dark energy to the dark matter component, but at present the dark energy component is dominating, and as we have mentioned that of W effective will re-enter the decelerating phase. But this may happen because of this reverse energy flow. And as the strength of interaction is very small and the evolution of Hubble parameter will also play an important role in the source term, this combined effect actually provides us with the correct result. So I'll conclude. So our motivation was to explore whether there is an interaction between this dark energy and dark matter sector, and we have found that the interacting dark energy models are consistent with observational data, but the flow of dark energy, the interaction is from the dark energy to the dark energy. However, it provides us the correct. Thank you.